I'm speaking to you about artificial general intelligence, AGI. Not just another tool, but potentially the first non-human mind to match or exceed our cognitive capabilities across every domain that matters. A technology that could fundamentally transform what it means to be human. This is not science fiction anymore. This is not some distant future concern. This is happening now in research labs around the world, in the algorithms that increasingly shape your daily life. And you, yes, you watching this, are living through what may be the most pivotal moment in human history since the development of language or agriculture. To understand what's coming, we need to understand where we are, how we got here, and where we might be headed. We need to look unflinchingly at both the promise and peril of creating minds potentially greater than our own. Think about what makes humans special. Our ability to reason abstractly, to learn from a few examples, to generalize knowledge across domains, to plan for the future, to understand ourselves and others, to create art that moves us, to build civilizations. Now imagine all of that capability, and more, embodied not in flesh and neurons but in silicon and code. Systems that never tire, never forget, can access all human knowledge instantly, and can improve themselves at a pace we can barely comprehend. The implications are staggering. AGI could help us solve our greatest challenges, from climate change to disease to poverty. It could usher in an era of abundance and discovery beyond our wildest dreams. Or, it could lead to the obsolescence of human labor, unprecedented concentration of power, the loss of human autonomy, even risks to our very survival as a species. The path we take isn't predetermined. It will be shaped by the choices we make today, as researchers, as companies, as governments, as a global society. And that's why understanding AGI, truly understanding it, matters so profoundly. Our journey begins with the most fundamental question of all. What is intelligence really? And how might we create it in a form other than our own? Before we can understand artificial general intelligence, we must first grapple with a more fundamental question: what is intelligence itself? Intelligence has proven notoriously difficult to define. We recognize it when we see it, yet struggle to capture its essence in words. Is it problem-solving ability? Adaptation to environment? The capacity to learn? Or honestly, is it something more ineffable? For centuries, philosophers and scientists have proposed different definitions, each capturing some aspect of this complex phenomenon. Aristotle saw it as the faculty of thought. Darwin understood it as adaptive behavior. Modern psychologists measure it through standardized tests. But intelligence isn't a single thing, it's a constellation of capabilities. Analytical intelligence helps us solve logical problems. Creative intelligence generates novel ideas. Emotional intelligence navigates social relationships. Practical intelligence applies knowledge to real-world situations. These capabilities emerge from distinct but interconnected systems in our brains. There's no single intelligence center. Rather, it's a complex interplay of perception, memory, reasoning, and more. Our attempts to measure intelligence have often been, well, kind of reductive. The intelligence quotient, or IQ test, developed in the early 20th century, primarily captures analytical and verbal abilities. It predicts academic success reasonably well, but honestly, it misses crucial dimensions of human capability. Someone with an average IQ might possess extraordinary creativity, emotional depth, or practical wisdom. Intelligence is multidimensional, and our measurements are incomplete at best. Moreover, intelligence isn't uniquely human. Crows fashion tools and solve multi-step puzzles. Octopuses navigate mazes and open jars. Dolphins recognize themselves in mirrors and communicate with complex vocalizations. Each species has evolved intelligence suited to its ecological niche. What makes human intelligence distinctive is its generality. We excel not at any single cognitive task, but at learning and adapting across an enormous range of domains. A human child can learn any language, master countless skills, and navigate novel social situations, all with the same brain. This generality allows us to transfer knowledge between domains. A principle learned in one context can be applied to another. A metaphor from one field can illuminate another. This cross-domain flexibility is really the hallmark of human intelligence. And this brings us to artificial intelligence. Most AI systems today possess narrow intelligence. They excel at specific tasks but fail completely outside their domain. A chess program can defeat grandmasters but can't recognize a cat. An image classifier can identify thousands of objects but can't hold a conversation. Artificial general intelligence, by contrast, would possess the same flexibility and generality that characterizes human cognition. It would be able to learn and perform any intellectual task that a human can. It would transfer knowledge between domains, adapt to novel situations, and potentially improve itself. More specifically, AGI would need to demonstrate several key capabilities. First, reasoning. That's the ability to draw logical conclusions, understand cause and effect, and solve novel problems. Second, learning, not just pattern recognition from massive datasets, but the ability to learn efficiently from limited examples, as humans do. Third, common sense, the vast background knowledge about how the world works that humans just take for granted. Fourth, planning. That's the ability to set goals and devise strategies to achieve them across multiple timescales. Fifth, communication. Understanding and generating natural language with all its nuance, ambiguity, and cultural context. And finally, self-awareness. Some degree of understanding of its own capabilities, limitations, and place in the world. How would we know when we've created AGI? Various tests have been proposed. The Turing test, conceived by Alan Turing in 1950, suggests that if a machine can fool human judges into believing it's human through conversation alone, it should be considered intelligent. But the Turing test has limitations. Modern language models can sometimes fool people briefly, yet clearly lack understanding of what they're saying. They're sophisticated pattern matchers, not truly intelligent systems. More rigorous tests have been proposed. The coffee test requires an AI to enter an unfamiliar house and figure out how to make coffee. The college student test requires it to enroll in a university and earn a degree. The employment test requires it to learn and perform an economically valuable job. So, different researchers actually define AGI in different ways, and these definitions have really important implications. OpenAI, for instance, defines it as AI systems that outperform humans at most economically valuable work, which is a definition that's really rooted in practical impact. On the other hand, DeepMind's Demis Hassabis focuses more on scientific discovery, suggesting that AGI would be able to make breakthroughs in mathematics or physics. The definition we choose actually matters a lot because it shapes what we build and how we evaluate it. If we define AGI purely in economic terms, we might create systems that maximize productivity but lack a deeper understanding. But if we define it in terms of scientific discovery, we might end up with brilliant problem solvers that, lack social intelligence. The gap between current AI and true AGI, honestly, remains pretty substantial. Today's most advanced systems excel in narrow domains, but they just lack the flexibility, common sense, and generality that really define human intelligence. Sure, they can recognize patterns in data, but they seriously struggle with things like causality, counterfactuals, and abstract reasoning. A human child, for example, can learn a new concept from just a few examples. They can reason about hypothetical situations they've never experienced, and they can understand the physical world, social dynamics, and even their own mental states. Current AI systems, they fall short on all these dimensions. Some researchers actually have proposed more nuanced frameworks for measuring machine intelligence. For instance, the collective intelligence test evaluates systems on their ability to collaborate with humans. The catastrophic forgetting test looks at whether systems can learn new skills without losing old ones. And then there's the generalization test, which assesses performance on tasks that are significantly different from the training data. It's worth noting that AGI doesn't necessarily need to replicate human intelligence exactly. Just as airplanes don't fly like birds but still achieve the same function, AGI might use different mechanisms than the human brain while achieving similar or even greater capabilities. The goal isn't to duplicate human cognition, but rather to create systems with comparable generality and flexibility. Human intelligence is also, deeply embodied and emotional. Our thinking is shaped by our physical experiences, our emotions, and our social connections. Whether AGI would need similar embodiment and emotional capacity, that still remains an open question. So when I talk about AGI throughout our journey together, I'm referring to artificial systems that can perform any intellectual task that humans can, with comparable or even greater proficiency. Systems that can learn, reason, plan, and communicate across domains, systems that in some meaningful sense understand the world and their place in it. With this understanding of intelligence in mind, let's explore how our quest to create artificial minds has evolved over time, from ancient myths to modern machine learning and the remarkable acceleration we're witnessing today. The dream of creating artificial minds is honestly as old as civilization itself. Ancient myths across cultures tell of human-like creations imbued with intelligence. In Greek mythology, Hephaestus crafted golden handmaidens that could think and speak. Jewish folklore tells of the golem, an artificial being animated from clay. In Hindu mythology, Brahma created artificial warriors called Mayas with extraordinary capabilities. These myths became, at least in part, realities through mechanical automata, devices that mimicked living creatures through intricate gears and mechanisms. In the 18th century, Jacques de Vaucanson created a mechanical duck that could eat, digest, and even defecate. The Turk, a famous chess-playing automaton, toured Europe defeating human opponents, though it secretly concealed a human chess master. The path to true artificial intelligence began with mathematics and logic. In the 17th century, Gottfried Wilhelm Leibniz dreamed of a universal calculus that could resolve all human disagreements through computation. In the 19th century, Charles Babbage designed the analytical engine, a mechanical computer that could be programmed with punched cards. Ada Lovelace, working with Babbage, recognized that such machines could manipulate symbols beyond just numbers. She wrote what's considered the first computer program and speculated that machines might someday compose music or create art, though she believed they could never truly originate anything. The formal foundations for AI emerged in the early 20th century. Bertrand Russell and Alfred North Whitehead attempted to formalize all of mathematics in their Principia Mathematica. Alan Turing developed the concept of a universal computing machine that could simulate any other computer's behavior. In 1950, Turing published Computing Machinery and Intelligence, proposing what became known as the Turing test and predicting that machines would eventually think. He addressed common objections to machine intelligence with remarkable foresight. But the field of artificial intelligence wasn't formally born until the summer of 1956, at a workshop at Dartmouth College. There, a group of young researchers including John McCarthy, Marvin Minsky, Claude Shannon, and Herbert Simon coined the term artificial intelligence and laid out an ambitious research agenda. Their proposal stated, "The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it." These pioneers were extraordinarily optimistic. Herbert Simon predicted in 1957, within 10 years a digital computer will be the world's chess champion, and within the visible future, machines will be capable of doing any work a man can do. Marvin Minsky declared in 1967 that within a generation, the problem of creating artificial intelligence will be substantially solved. The early years saw remarkable progress. Programs like Logic Theorist proved mathematical theorems. ELIZA simulated conversation through simple pattern matching. Shard-Lu manipulated blocks in a virtual world based on natural language commands. This early work focused on symbolic AI, explicitly programming rules and representations that machines could manipulate. The assumption was that human knowledge could be formalized as symbols and logical rules which computers could then process to produce intelligent behavior. But the field soon encountered major obstacles. Problems that seemed simple for humans, like recognizing objects or understanding context, proved extraordinarily difficult to solve with explicit rules. Funding dried up, and the first AI winter descended in the 1970s as initial promises failed to materialize. So, a revival came in the 1980s with expert systems. These were programs containing specialized knowledge in domains like medicine or geology. For example, MySyn could diagnose blood infections, and Prospector actually helped discover a molybdenum deposit worth $100 million. Companies, invested heavily in this approach, but expert systems also hit limitations. They were really brittle, failing completely when faced with situations outside their programmed knowledge. They just couldn't learn from experience or adapt to new domains. A second AI winter followed in the late 1980s and early 1990s. Meanwhile, an alternative approach was slowly developing. Instead of explicitly programming knowledge, researchers began to explore systems that could actually learn from data. Neural networks, which were inspired by the brain's structure, showed promise, but they were limited by computing power and data availability at the time. specialized AI continued to advance. In 1997, IBM's Deep Blue defeated world chess champion Garry Kasparov, fulfilling Simon's prediction, though it happened about 30 years late. But, this wasn't general intelligence. Deep Blue was a specialized chess machine that couldn't even recognize a chessboard in the physical world. The internet changed everything. Suddenly, vast amounts of data became available for training learning systems. And of course, computing power just kept increasing exponentially, following Moore's law. The stage was set for a revolution. That revolution arrived in 2012, when a neural network created by Geoffrey Hinton's team dramatically outperformed traditional approaches in the ImageNet competition for image recognition. This really marked the beginning of the deep learning era that we see continuing today. In 2016, another watershed moment occurred when DeepMind's AlphaGo defeated world champion Lee Sedol at the ancient game of Go, a feat that many experts thought was still decades away. The machine made a move so creative, so unexpected, that commentators actually thought it was a mistake at first. But it wasn't. It was a glimpse of something new. Since then, progress has accelerated at a dizzying pace. In 2020, OpenAI's GPT-3 demonstrated remarkable language capabilities. And in 2022, systems like DALL-E and Stable Diffusion began generating images from text descriptions with astonishing quality. By 2023, GPT-4 showed capabilities across language, reasoning, and multimodal understanding that surprised even its creators. Today's AI systems can write essays, create art, compose music, program software, and engage in conversations that honestly feel remarkably human. They can solve scientific problems, help design new materials, and assist in medical diagnosis. The gap between specialized AI and general intelligence really does seem to be narrowing. This acceleration shows no signs of slowing. In fact, it's speeding up. Capabilities that seemed impossible 5 years ago are now commonplace. Systems improve not in decades or years but in months or weeks. The race to develop advanced AI has become global. In the United States, companies like OpenAI, Google DeepMind and Anthropic have raised billions of dollars. China has declared AI a national priority, with companies like Baidu and SenseTime receiving massive government support. The European Union, Japan and others are also investing heavily. This progress is powered by unprecedented computational resources. Training the most advanced AI models requires energy equivalent to what thousands of homes use annually. The largest models process trillions of words and images, learning patterns that would take human lifetimes to absorb. A key insight driving recent progress is that neural networks scale predictably. As we increase model size, training data, and computing power, capabilities improve following mathematical patterns. Some researchers believe that continued scaling of existing approaches might be sufficient to reach AGI, but scaling alone may not be enough. Current systems still lack core aspects of human intelligence: causal reasoning, common sense, truly understanding the world, rather than just manipulating symbols. We may need fundamental breakthroughs, not just bigger versions of today's models. Predictions about when we might achieve AGI vary wildly. Some experts believe we're already seeing early forms of AGI in today's most advanced systems. Others think we're still decades away from true general intelligence. The median estimate from AI researchers in recent surveys points to the 2040s, but with enormous uncertainty. What's clear is that we're in the midst of an AI revolution unlike anything in history. The pace of progress has surprised even experts in the field, and the systems being developed today are already transforming our world in ways both subtle and profound. But to understand how we might bridge the remaining gap from today's specialized AI to true artificial general intelligence, we need to examine the architecture of intelligence itself, the capabilities that AGI would need, and the approaches that might get us there. Now that we understand what intelligence is and how AI has evolved, let's explore the different pathways that might lead to artificial general intelligence. There isn't just one road to AGI. There are multiple approaches, each with its own philosophical assumptions, technical challenges, and implications. The quest for AGI really resembles the early days of flight. Some pioneers studied birds meticulously, believing the secret lay in mimicking nature. Others took entirely different approaches, focusing on principles like lift and propulsion rather than flapping wings. Similarly, AGI researchers diverge on whether we should closely emulate the human brain or forge entirely new paths to intelligence. let's examine the major approaches that could potentially lead to AGI, understanding that the ultimate solution might combine elements from several of these paths. The first and currently dominant approach is what's called the scaling hypothesis. This view suggests that continued scaling of neural networks, making them larger, training them on more data with more computing power, will eventually lead to AGI. The core idea is that intelligence emerges at scale, just as complex behaviors emerge in other systems when they grow sufficiently large. We've already seen remarkable emergent capabilities as models scale up. Early language models could barely form coherent sentences. Today's largest models can write essays, solve novel problems, and exhibit behaviors their creators didn't explicitly program. Each increase in scale has brought surprising new abilities. What's fascinating about scaling laws is their predictability. We can plot how performance improves as we increase model size, data, and compute. And these relationships follow remarkably consistent mathematical patterns. This suggests we might be on a predictable path toward AGI if we can continue scaling. However, scaling faces significant challenges. The computational requirements grow exponentially, with costs and energy usage becoming prohibitive. There may also be diminishing returns. Each doubling of model size brings smaller improvements than the last. And some cognitive capabilities might not emerge from scale alone. A second approach is neuromorphic computing, building systems that more closely mimic the structure and function of the human brain. While today's neural networks were loosely inspired by the brain, they differ dramatically in architecture and operation. Biological neurons are vastly more complex than the simplified artificial neurons in current AI systems. They operate through intricate biochemical processes, with thousands of connections per neuron and dozens of different neurotransmitters. The brain also has a highly specialized architecture, with different regions evolved for specific functions. Neuromorphic researchers are developing hardware and algorithms that capture more of this biological complexity. Companies like Intel and IBM have created specialized neuromorphic chips that process information more like the brain, with potential advantages in energy efficiency and learning capability. A third approach involves hybrid systems that combine neural networks with symbolic AI. Remember that early AI focused on explicit symbols and rules, while modern deep learning focuses on pattern recognition from data. Each has strengths and weaknesses. Neural networks, really excel at perception, pattern recognition, and learning from examples. But honestly, they struggle with logical reasoning, planning, and explicit knowledge representation. They're also, black boxes whose decision-making processes can be opaque. Symbolic systems, conversely, excel at logical reasoning and transparent decision-making, but struggle with perception and learning from unstructured data. They require human programmers to explicitly encode knowledge and rules. Hybrid approaches aim to get the best of both worlds, the perceptual and learning capabilities of neural networks combined with the reasoning and transparency of symbolic systems. Systems like IBM's Watson and various neurosymbolic architectures represent this approach. A fourth pathway uses evolutionary algorithms. Rather than designing intelligence directly, this approach sets up conditions for it to evolve through processes similar to natural selection. Virtual organisms compete and reproduce based on their performance at cognitive tasks, with successful traits passing to the next generation. This approach has shown remarkable success in specific domains. Algorithms evolved through this process have designed efficient antennas, discovered new drug molecules, and created game-playing strategies that surprise human experts. The advantage is that evolution can discover solutions humans might never think of. A fifth approach is whole brain emulation. This ambitious pathway aims to scan and digitally reconstruct an entire human brain at the neural level. Rather than building intelligence from scratch, it would copy an existing intelligence, potentially preserving all the capabilities of the original. This requires technologies far beyond our current capabilities. We would need to scan a brain at resolutions capturing individual synapses and their properties, then simulate all these components and their interactions. Projects like the Human Brain Project and various connectomy mapping efforts are early steps in this direction, but true whole brain emulation remains distant. Perhaps the most intriguing pathway is recursive self-improvement. This approach focuses on creating AI systems that can improve their own code, essentially programming themselves to become smarter. Once an AI reaches a certain threshold of capability, it could potentially trigger an intelligence explosion as it repeatedly enhances itself. This pathway is both promising and, well, concerning. If achieved, it could rapidly lead to superintelligence far beyond human levels. But it also raises some really profound control and safety questions. How do we ensure such systems remain aligned with human values through multiple generations of self-modification? Beyond these specific approaches, most researchers agree that true AGI will need to be multimodal, able to process and integrate information across different types of data and sensory inputs. Human intelligence seamlessly combines vision, hearing, touch, and other senses with abstract reasoning and knowledge. AGI would likely need similar integration. The role of embodiment remains debated. Some researchers believe that intelligence requires a physical body interacting with the world, that cognition is fundamentally grounded in sensor-motor experience. Others argue that disembodied systems could achieve general intelligence through simulation or abstract reasoning alone. Different regions and research groups, really emphasize different approaches. American companies like OpenAI and Anthropic have focused heavily on scaling large language models. DeepMind combines neural networks with reinforcement learning. European researchers often emphasize hybrid neurosymbolic systems and, ethical considerations. Chinese efforts span multiple approaches with significant government coordination. The most likely path to AGI probably combines elements from multiple approaches. We might need the pattern recognition of neural networks, the reasoning capabilities of symbolic systems, the efficiency of neuromorphic computing, and architectural insights from cognitive science. The breakthrough could come from unexpected combinations rather than any single approach. The time frame for AGI development depends heavily on which pathway proves most fruitful. If scaling laws continue to hold and computing power continues to increase, we might see AGI-level capabilities emerge within a decade. If fundamental new breakthroughs are required, the timeline could be much longer. What's certain is that the race toward AGI has accelerated dramatically. Billions of dollars are flowing into research. Talented scientists and engineers are flocking to the field. Computing resources are being marshaled at unprecedented scale. Whether AGI arrives in years or decades, the pathways are being built now. But what specific capabilities would a true AGI need? Let's break down the core components of general intelligence and, examine how close current systems are to achieving each one. Artificial general intelligence isn't a single breakthrough but a constellation of capabilities working in concert. To understand how close we are, and the challenges that remain, we need to examine each of these capabilities in depth. At the heart of intelligence lies reasoning, the ability to think logically, understand cause and effect, and solve novel problems. Human reasoning takes multiple forms, each with distinct characteristics and challenges for AI. Deductive reasoning moves from general principles to specific conclusions. If all humans are mortal and Socrates is human, then Socrates is mortal. Current AI systems can perform basic deductive reasoning when the premises are clearly stated, but honestly, they struggle with implicit assumptions that humans take for granted. Inductive reasoning moves from specific observations to general principles, seeing patterns and forming hypotheses. Modern machine learning excels at this type of reasoning, finding patterns in data that might escape human notice. However, these systems can also find spurious correlations or be misled by biased training data. Abductive reasoning seeks the most likely explanation for observations, the kind of thinking detectives and doctors use. This remains challenging for AI, requiring both background knowledge and the ability to weigh competing explanations. Particularly difficult is causal reasoning, understanding not just that events correlate but that one causes another. Most current AI systems capture statistical associations but struggle with true causality. They can tell you that umbrellas and rain appear together, but not that rain causes people to use umbrellas rather than vice versa. Even more challenging is counterfactual reasoning, thinking about what would have happened if circumstances were different. If I hadn't missed the bus, would I have arrived on time? This requires a mental model of how the world works that can be manipulated to explore alternative scenarios. Planning, the ability to set goals and devise strategies to achieve them, represents another crucial aspect of reasoning. While specialized AI systems can plan in restricted domains like games, general planning across diverse real-world scenarios remains elusive. Mathematical reasoning deserves special attention. Mathematics represents perhaps the purest form of human reasoning. yet remains surprisingly difficult for AI. Recent systems have made progress in solving mathematical problems, but still fall short of human mathematicians in proving new theorems or developing novel concepts. Current AI systems show both impressive capabilities and striking limitations in reasoning. They can solve some complex problems, but fail at seemingly simple tasks that require common sense. They can follow explicit logical steps, but struggle to determine which facts are relevant to a given situation. A hallmark of general intelligence is generalization, the ability to apply knowledge and skills beyond the specific contexts in which they were learned. This is where current AI systems often fall short. Transfer learning represents one approach to generalization. Rather than learning each task from scratch, a system applies knowledge from one domain to accelerate learning in another. For example, an AI trained to recognize cats might transfer some of that knowledge to recognizing dogs. Even more impressive are few-shot and zero-shot learning, the ability to perform new tasks with minimal or no specific training examples. Humans excel at this. A child who knows what a zebra is can recognize one on first sight, even if they've never seen one before. So, recent large language models have shown some pretty surprising zero-shot capabilities, you know? They can perform tasks they weren't explicitly trained on. But, well, their performance usually lags far behind systems that are specifically trained for those tasks. And honestly, they can fail unpredictably when faced with novel challenges. A critical limitation here is what's called out-of-distribution generalization. Basically, systems trained on one data distribution often fail catastrophically when they're faced with examples that differ significantly from their training data. For example, a self-driving car trained in sunny California might fail in snowy conditions. And an image recognition system trained on professional photography might just not work on hand-drawn sketches. Underlying these challenges is, the deeper problem of abstraction and concept formation. Humans naturally form abstract concepts that capture the essence of things while ignoring irrelevant details. For instance, we understand that transportation includes cars, boats, and spaceships, even though they look really different on the surface. Current AI systems, well, they really struggle with this level of abstraction. Sure, they can recognize patterns, but they have difficulty forming the kind of flexible, hierarchical concepts that humans use to make sense of the world. They lack what cognitive scientists call intuitive theories. Those frameworks that organize knowledge and guide reasoning across different domains. Memory forms another crucial component of intelligence. It's not just about storing information, but also about organizing, retrieving, and updating it appropriately. Human memory, actually takes multiple forms, each with its own distinct properties. Working memory holds information temporarily for immediate use, like, say, remembering a phone number just long enough to dial it. It's limited in capacity, but it's absolutely crucial for complex reasoning. Current AI systems don't really have the same capacity limitations as humans, but they often lack the dynamic, attention-based properties of human working memory. Long-term memory stores information over extended periods. In humans, this includes episodic memory, which is about personal experiences, semantic memory for facts and concepts, and procedural memory for skills and habits. AI systems, they can store vast amounts of information, but they still struggle with the flexible, context-sensitive retrieval. That really characterizes human memory. So, memory consolidation, the process of transferring information from short-term to long-term storage, actually happens during sleep in humans. AI systems, on the other hand, undergo similar processes during training, but, the mechanisms are really quite different. Understanding these differences could, lead to more efficient and effective AI learning. Context-dependent memory retrieval represents a particular challenge. Humans naturally recall different information depending on the current situation and goals. But AI systems often lack this kind of contextual sensitivity, either retrieving way too much irrelevant information or sometimes failing to access the knowledge that's actually needed. Interestingly, forgetting is as important as remembering. Human memory selectively preserves important information. While, allowing irrelevant details to fade, this prevents cognitive overload and actually allows for generalization. AI systems that never forget can, in fact, perform worse than those with strategic forgetting mechanisms. Recent advances in AI memory architectures include attention mechanisms, external memory banks, and retrieval-augmented generation. These approaches allow systems to access relevant information more efficiently and maintain coherence over longer contexts. Despite these advances, current AI memory systems still lack the richness and flexibility of human memory. They struggle with episodic memory, have difficulty integrating new information with existing knowledge, and often fail to retrieve relevant facts in appropriate contexts. Perception, the ability to interpret sensory information, forms the foundation of intelligence. For humans, this includes vision, hearing, touch, taste, and smell, all processed by specialized brain regions and integrated into a coherent understanding of the world. Computer vision has made remarkable progress. Modern systems can recognize thousands of object categories, detect faces with superhuman accuracy, and generate photorealistic images from text descriptions. In controlled settings, they often outperform humans on specific perceptual tasks. Similarly, audio processing has advanced dramatically. Speech recognition now approaches human-level accuracy in many contexts. Systems can identify speakers, detect emotions from voice, and even isolate specific sounds in noisy environments. Multimodal integration, combining information across sensory modalities, represents a frontier in AI perception. Recent systems can understand relationships between images and text, generate images from descriptions, or describe scenes in natural language. This integration is crucial for grounding language in perceptual reality. However, significant challenges remain in grounding perception in physical reality. AI systems trained on images or videos often lack understanding of three-dimensional space, physics, and, object permanence. A system might recognize a cup in an image without understanding that it can contain liquid, or that it continues to exist when not visible. Interestingly, AI perception differs from human perception in fundamental ways. Systems can be fooled by adversarial examples, subtle manipulations invisible to humans that cause a catastrophic misclassification. Conversely, they may be immune to optical illusions that reliably fool humans. Current perceptual systems also struggle with unusual scenarios not well represented in their training data. They may fail to recognize objects in unusual orientations, lighting conditions, or contexts. They typically lack the robust common-sense physics that allows humans to understand how objects interact in the physical world. This brings us to the question of embodiment, the role of physical bodies in intelligence. Humans develop intelligence through bodily interaction with the environment. We learn about gravity by dropping things, about causality by pushing objects, about spatial relationships by moving through space. Some researchers argue that true intelligence requires similar embodiment, that an AI must interact with the physical world to develop genuine understanding. Robotics research explores this approach, creating systems that learn through physical interaction rather than passive observation. Physical manipulation presents particular challenges, grasping diverse objects, applying appropriate force, and performing dexterous manipulation remain difficult for robots despite decades of research. The sensoromotor coordination that humans take for granted requires integrating perception, planning, and control in real time. However, physical embodiment isn't the only possibility. Digital embodiment in simulated environments might provide many of the same benefits. Virtual agents can interact with simulated physics, learn from consequences, and develop spatial understanding without physical bodies. The simulation gap presents a significant challenge. Systems trained in simulation often perform poorly when transferred to the real world, due to subtle differences between simulated and physical reality. Bridging this gap remains an active research area. Some researchers question whether embodiment is necessary at all for certain aspects of intelligence. Abstract reasoning, language understanding, and many cognitive tasks might be achievable without direct physical interaction. After all, humans can think about concepts like infinity that have no physical manifestation. Embodiment is essential. Without grounding in physical experience, systems will never truly understand concepts like above, heavy, or fragile. They'll just be manipulating symbols without meaning. That's too limiting. Humans born without sight or hearing develop rich intelligence through other modalities. AGI might develop through entirely different pathways than human intelligence. The most promising approaches may combine elements of physical and virtual embodiment, allowing systems to learn from both real and simulated experiences, while developing abstract reasoning capabilities that transcend specific embodiments. At the core of intelligence lies learning, the ability to improve performance based on experience. Learning takes many forms, each with distinct characteristics and applications in AI. Supervised learning, learning from labeled examples, has driven much of the recent progress in AI. A system is shown inputs paired with correct outputs like images labeled cat or dog and, learns to predict outputs for new inputs. This approach powers image recognition, speech transcription, and honestly, so many other applications. Unsupervised learning works without explicit labels, finding patterns and structure in data. This includes clustering similar items, reducing dimensionality of complex data, and learning representations that capture underlying features. It's actually closer to how humans learn in many contexts. Discovering patterns without explicit instruction. Reinforcement learning involves learning through interaction with an environment, receiving rewards or penalties based on actions. This approach has achieved remarkable results in games like chess, Go, and Atari, as well as robotics and resource management. It really captures the trial-and-error nature of much human learning. Self-supervised learning represents a powerful recent development. Basically, systems generate their own supervision signals from data, for example by masking words in a sentence and then learning to predict the missing words. This, allows learning from vast amounts of unlabeled data and has powered recent advances in language models. Meta-learning, or learning to learn, represents a higher level of sophistication. Instead of just learning specific tasks, a system learns strategies for learning new tasks more efficiently. This, in a way, captures the human ability to become better learners over time, applying past learning experiences to new domains. Curriculum learning kind of mimics how humans learn through progressively more difficult challenges. Rather than tackling complex problems immediately, systems start with simple cases, and then gradually advance to more difficult ones. This approach can honestly dramatically improve learning efficiency and final performance. So, social learning, basically learning from observation and imitation, plays a really crucial role in human development. Children learn not just from direct experience but also from watching others. Interestingly, AI systems are starting to show similar capabilities, learning from demonstrations or even from observing other AI systems. A significant challenge in AI learning is what we call catastrophic forgetting. That's the tendency to lose previously acquired knowledge when learning new tasks. Now, humans can learn new skills without forgetting old ones. But neural networks, they often overwrite previous learning. Unless they're specifically designed to prevent this. Continual learning is aimed at addressing this challenge, allowing systems to accumulate knowledge over time without forgetting. Some approaches include regularization techniques that help preserve important parameters, replay mechanisms that revisit previous experiences, and modular architectures that allocate new resources for new tasks. Sample efficiency represents another crucial difference between human and AI learning. Humans can often learn from just a few examples, while current AI systems typically require thousands or even millions. Bridging this gap would represent a major advance toward AGI. Understanding what and how AI systems learn remains challenging. Honestly, many modern systems are black boxes whose internal representations and decision processes are opaque even to their creators. Explainable AI research aims to develop systems whose learning and reasoning can be understood and verified by humans. These 6 capabilities, reasoning, generalization, memory, perception, embodiment, and learning, form the foundation of general intelligence. Current AI systems show impressive abilities in specific areas. But, well, they lack the integration and flexibility that characterize human cognition. True AGI would require not just advances in each capability, but their seamless integration into a coherent whole. A system that can perceive the world, learn from experience, remember relevant information, generalize across domains, reason about novel situations, and potentially interact with the physical environment. With this understanding of AGI's architecture, let's examine the signs of emergence we're already seeing, and the possibility of an intelligence explosion that could transform our world. We've explored the architecture of intelligence, and the capabilities AGI would need. But how close are we really to achieving artificial general intelligence? What signs of emergence are we already seeing? And what remains beyond our grasp? The pace of AI advancement has surprised even experts in the field. Capabilities that seemed decades away have arrived in years or even months. Systems are demonstrating abilities their creators didn't explicitly program. Emergent behaviors that hint at deeper understanding. Large language models represent perhaps the most striking example. Originally designed to predict text, these systems now demonstrate capabilities far beyond their training objectives. They can write essays, generate code, translate languages, answer questions, and even reason through complex problems. Consider GPT-4, released in 2023. It can pass the bar exam, score in the 90th percentile on the SAT, write functioning computer programs in multiple languages, and engage in nuanced conversations across countless topics. It can understand jokes, detect sarcasm, and generate creative content across various styles and formats. Multimodal models represent another leap forward. Systems like DALL-E, Midjourney, and Stable Diffusion can generate images from text descriptions with remarkable fidelity. More advanced models can understand relationships between text and images, answer questions about visual content, and even generate videos from text prompts. Autonomous agents push these capabilities further. Rather than responding to specific prompts, these systems can set their own goals, make plans to achieve them, and take actions in digital or physical environments. They can use tools, adapt to changing circumstances, and learn from their experiences. Tool use represents a particularly significant development. Recent systems can recognize when they need external tools, like calculators for precise math, search engines for current information, or code interpreters for computational tasks, and use them appropriately. This dramatically extends their capabilities beyond their internal knowledge. Planning capabilities have also advanced significantly. Systems can break down complex tasks into manageable steps, anticipate potential obstacles, and adjust plans as circumstances change. While still limited compared to human planning, these abilities enable much more sophisticated problem-solving than earlier AI. What's remarkable about these emergent capabilities is that we didn't explicitly program them. They arise from scale and architecture rather than specific design choices. This suggests we may be approaching a threshold where increasingly general intelligence emerges naturally from sufficiently advanced systems. Traditional AI benchmarks are being rapidly conquered. Systems have surpassed human performance on standardized tests, image recognition challenges, and even some creative tasks. Each year, benchmarks that seem challenging become routine, requiring the development of more difficult tests. This has led to what some call the moving goalpost problem. Tasks once considered hallmarks of intelligence, like playing chess or translating languages, are dismissed as mere computation once machines master them. The definition of intelligence shifts to encompass whatever remains beyond AI's current capabilities. Yet significant limitations remain. Current systems still struggle with robust common-sense reasoning, causal understanding, and out-of-distribution generalization. They can generate plausible-sounding but factually incorrect information, a phenomenon called hallucination. And, they lack true understanding of the physical world and its constraints. Perhaps most tellingly, they lack the sample efficiency and transfer learning abilities of human children. A child can learn a new concept from just a few examples and apply it in novel contexts. But current AI typically requires thousands or even millions of examples. And honestly, it struggles to transfer knowledge between domains. The question of how close we are to AGI really divides experts. Some believe we're seeing proto-AGI already in today's most advanced systems, that continued scaling and refinement of current approaches will lead to general intelligence within years. Others argue that, fundamental breakthroughs are still needed to bridge the remaining gaps. A 2022 survey of AI researchers found the median estimate for achieving human-level AGI was 2059, but with enormous variation, from 2030 to beyond 2100. This wide range reflects genuine uncertainty about both the pathways to AGI and the nature of intelligence itself. What's clear is that we're in uncharted territory. Systems are developing capabilities that surprise their creators, operating in ways we don't fully understand, and advancing at a pace that, honestly, challenges our ability to predict and govern their development. This brings us to a profound question. What happens if this acceleration continues? What if AI systems become capable of improving themselves, triggering a feedback loop of ever-increasing intelligence? This possibility, known as an intelligence explosion, could transform our world in ways we can barely imagine. In 1965, mathematician and cryptologist I.J. Good wrote a short passage that would become one of the most influential and concerning predictions about artificial intelligence. Let an ultra-intelligent machine be defined as a machine that can far surpass all the intellectual activities of any man, however clever. Since the design of machines is one of these intellectual activities, an ultra-intelligent machine could design even better machines. There would then unquestionably be an intelligence explosion, and the intelligence of man would be left far behind. This is the concept of recursive self-improvement. An AI system that can enhance its own capabilities could make itself smarter. That smarter version could make itself smarter still. Each iteration would be faster and more capable than the last, potentially leading to an exponential increase in intelligence. To understand this possibility, we need to grasp the power of exponential growth. Our brains evolved to think linearly, one step after another. But many processes in nature and technology follow exponential patterns where growth rates themselves increase over time. 30 steps linearly, 1, 2, 3, 4 and so on gets you to 30. 30 steps exponentially, 1, 2, 4, 8 and so on gets you to over a billion. This is why technologies like computing power, DNA sequencing and renewable energy have transformed our world so rapidly. Each follows exponential improvement curves. We're already seeing exponential patterns in AI development. Performance on benchmarks improves not gradually but in sudden leaps. Capabilities that seemed decades away arrive in years or months. Each new system builds on the insights and data from previous generations. The key difference with AGI would be self-improvement. Today's AI systems are created and improved by human engineers. An AGI capable of understanding its own design could potentially improve itself without human intervention, creating a positive feedback loop of increasing capability. How might this intelligence explosion unfold? Experts debate the likely speed and trajectory. Some envision a fast takeoff scenario where AGI rapidly bootstraps itself to superintelligence within days or hours once a critical threshold is reached. Others predict a slow takeoff with more gradual improvement over years or decades. The mathematics of exponential growth tells us that even a slow initial pace can lead to dramatic acceleration. If an AGI could improve its capabilities by just 10% per year through self-modification, it would double its intelligence every 7 years. At 10% per month, it would double every 7 months. At 10% per day, which isn't implausible for a digital system, it would double every week. So, several factors could limit or constrain an intelligence explosion. Hardware represents one potential bottleneck. Even a self-improving AI would, be limited by the physical computers it runs on. Designing better hardware and manufacturing it actually takes time and resources that might slow the feedback loop. Diminishing returns present another potential constraint. Each increment of improvement might require exponentially more resources than the last. Just as human scientific progress often requires increasingly complex experiments and larger teams, AI self-improvement might face similar scaling challenges. There may also be fundamental limits to intelligence itself. Thresholds beyond which further improvements yield minimal practical advantage. Some argue that intelligence, like other natural phenomena, must eventually reach physical or logical limits. However, history suggests that apparent limits are often overcome through paradigm shifts. The Wright brothers achieved flight not by building better gliders, but by adding engines. Similarly, an AGI might overcome apparent limits through novel approaches rather than just incremental improvements. The concept of phase transitions offers a useful analogy. Water remains liquid as temperature increases until, suddenly, it transforms to steam at 100 degrees Celsius. Intelligence might, similarly experience discontinuous jumps when critical thresholds are reached rather than smooth, predictable progress. This debate between continuists, who expect gradual progress, and discontinuists, who expect sudden leaps, has profound implications. If AGI development will proceed smoothly with clear warning signs, we have time to adapt our governance and safety measures. But if it might undergo sudden phase transitions, we really need to prepare well in advance. Predictions about when an intelligence explosion might occur, they really vary wildly. Some experts believe the necessary foundations already exist in today's most advanced systems and, honestly, we could see the beginnings of recursive self-improvement within just a few years. Others think we're still decades away from reaching that critical threshold. Ray Kurzweil, who's known for his technological predictions, has actually forecast that AGI will be achieved around the year 2029. With a technological singularity, a point beyond which technological progress becomes so rapid that predictions break down, occurring around 2045. Other researchers are, more cautious. They point to the many challenges still facing AI systems, from common-sense reasoning to robust generalization, and argue that these represent fundamental obstacles rather than just mere engineering problems. The truth likely lies somewhere in between these extremes. What's clear is that the possibility of an intelligence explosion represents both unprecedented opportunity and risk. A rapidly self-improving AGI could help solve humanity's greatest challenges, or honestly pose an existential threat if its goals don't align with our own. Whether it arrives through gradual progress, or a sudden breakthrough, AGI would, without a doubt, transform human society at its foundations. Let's take a moment to examine these potential impacts on our economy, our identity, and the power structures that govern our world. Throughout history, technological revolutions have transformed not just how we work, but the very structure of our economies and societies. The agricultural revolution allowed us to settle in permanent communities. The Industrial Revolution moved millions from farms to factories. The digital revolution connected humanity through global networks. But the AGI revolution may be different, in both scale and speed. Previous technological transitions played out over generations. Children could train for different careers than their parents. Societies had time to adapt institutions and safety nets. The AGI revolution may unfold within a single generation, potentially transforming the economy faster than our social systems can respond. Already AI is automating tasks across the economic spectrum. It's not just routine physical labor anymore. Systems can write articles, create artwork, diagnose diseases, trade stocks, and even generate code. As these capabilities expand toward AGI, few if any jobs would remain beyond the reach of automation. Let's examine which sectors might be transformed first, and how the economic landscape could evolve as AGI capabilities advance. Transportation and logistics represent an early frontier. Self-driving vehicles are already being tested on public roads. Automated drones are delivering packages. Warehouses operate with minimal human intervention. Once these technologies mature, millions of driving and logistics jobs could be transformed or eliminated. Knowledge work, once considered safe from automation, is increasingly vulnerable. AI systems can process legal documents, write reports, analyze data, and generate creative content. As these capabilities improve, roles from paralegals to financial analysts to content creators face significant disruption. Healthcare presents a more complex picture. AI can already outperform human radiologists at detecting certain conditions and assist in diagnosing diseases. But the human elements of care, empathy, judgment, and ethical decision-making remain crucial. The likely outcome is augmentation rather than wholesale replacement, with AI handling routine cases and analysis, while humans focus on complex care and emotional support. Creative fields face similar dynamics. AI can generate impressive art, music, and writing. But human creativity involves more than just pattern recognition. It draws on lived experience, cultural context, and intentionality. The boundary between human and machine creativity will likely blur, with AI serving as a creative partner rather than a replacement. Manufacturing and construction have already seen significant automation, but AGI would accelerate this trend dramatically. Robots with general-purpose capabilities could adapt to different tasks without reprogramming. Three-dimensional printing and automated construction could transform how we build everything from consumer products to buildings. Education might be revolutionized through personalized AI tutors that adapt to each student's learning style, pace, and interests. This could democratize access to high-quality education while transforming the role of human teachers toward mentorship, inspiration, and social-emotional development. The key difference from previous technological revolutions is that AGI could potentially perform any cognitive task. In the past, automation created new types of jobs even as it eliminated others. But if machines can do everything humans can do, only better, faster, and cheaper, what economic role remains for human labor? Optimists point to history, how technological revolutions have ultimately created more jobs than they destroyed. The Industrial Revolution eliminated many agricultural jobs but created factory work. The Digital Revolution reduced manufacturing employment in developed countries but created vast new sectors in software, services, and creative industries. New job categories are already emerging: prompt engineers who craft instructions for AI systems, AI trainers who provide feedback to improve performance, AI ethicists who address bias and safety concerns, and AI human collaboration specialists who design workflows combining human and machine capabilities. However, the transition will likely be uneven and potentially painful. We're already seeing job polarization, growth in both high-skilled, high-wage jobs and low-skilled, low-wage jobs, with hollowing out of middle-skill occupations. The pace of change presents a particular challenge. Even if new jobs eventually emerge, the transition period could see widespread displacement faster than workers can retrain. Someone who spent decades developing specialized skills might find them suddenly obsolete, with few obvious paths forward. This has sparked renewed interest in lifelong learning and educational innovation. Traditional four-year degrees designed for careers spanning decades may give way to continuous education models with shorter, more focused training modules that allow workers to adapt to rapidly changing demands. More radical proposals include universal basic income, providing everyone with enough to meet basic needs regardless of work. Pilot programs around the world are testing this approach, with mixed results. Proponents argue it would provide a safety net during economic transition and recognize the value of non-market activities like caregiving and community service. Other proposed models include job guarantees, reduced working hours, stakeholder capitalism, and various forms of wealth sharing. Each attempts to address a fundamental question: in an economy where traditional labor may no longer be the primary source of value, how do we ensure widespread prosperity? This question becomes particularly urgent given current trends toward concentration of wealth and power. The 5 largest tech companies already have market capitalizations exceeding the GDP of most nations. AGI could accelerate this concentration, with ownership of increasingly capable systems conferring enormous economic advantage. Data represents another crucial resource in the AGI economy. Systems learn from data, and those with access to more and better data gain competitive advantages. This raises questions about data ownership, compensation for data creators, and the potential for data monopolies. The global distribution of benefits and disruption will likely be uneven. Countries with strong technology sectors, educational systems, and social safety nets may adapt more successfully than those dependent on labor-intensive industries or lacking robust institutions. The timeline for these economic transformations depends heavily on how AGI capabilities develop. A gradual progression would allow more time for adaptation. A sudden breakthrough could trigger rapid, widespread disruption before social systems can respond. What's clear is that we face profound economic questions that go beyond technology itself. How do we distribute the enormous productivity gains AGI could create? How do we ensure that automation serves human flourishing rather than merely maximizing profit? How do we redefine meaningful work and contribution in a world where traditional labor may no longer be central to the economy? These economic questions lead naturally to deeper ones about human identity and purpose. In a world where machines can do everything we do and more, what does it mean to be human? What gives our lives meaning and value? For most of human history, work has been central to our identity. We introduce ourselves by our professions. We spend most of our waking hours working. We derive meaning, status, and social connections from our jobs. I'm a teacher, I'm a doctor, I'm an engineer. These statements aren't just about how we earn money. They express who we are, how we contribute to society, and what gives our lives purpose. This centrality of work is relatively recent in human history. Hunter-gatherers typically worked fewer hours than modern humans, with more time for community, ritual, and leisure. Medieval peasants followed seasonal rhythms with periods of intense labor and periods of celebration. The modern work ethic, with strict separation of work and leisure and moral value attached to productivity, emerged largely with industrial capitalism. As AGI systems become capable of performing any cognitive task, this work-centered identity faces a profound challenge. If machines can teach, diagnose, design, and create, often better than humans, what becomes of our occupational identities? What happens to our sense of purpose when our traditional contributions are no longer needed? I spent 30 years becoming an expert radiologist. I was respected, well-paid, and most importantly, I saved lives. Now an AI can detect cancer more accurately than I can. I still have a job, overseeing the AI and handling complex cases, but it's not the same. Something fundamental has changed about how I see myself and my contribution. Some envision a post-work society where automation liberates humans from drudgery, allowing us to focus on creativity, relationships, and self-development. In this view, AGI could enable a new renaissance, with humans freed to pursue art, science, philosophy, and community without economic pressure. This isn't entirely unprecedented. Throughout history, privileged classes freed from manual labor have often contributed disproportionately to cultural and intellectual advancement. The difference would be democratizing this privilege, extending it beyond elites to society as a whole. Already, many find their deepest meaning outside traditional employment, in raising children, creating art, volunteering, pursuing spiritual practices, building communities, or exploring nature. These activities might become more central to identity in a world where traditional work is less available or necessary. However, work provides more than just meaning. It confers status and social position. Throughout history, humans have organized hierarchies based on contribution and capability. If traditional accomplishments become automated, how will social status be determined? What new hierarchies might emerge? We're already seeing new status markers emerge: influence on social media, rare digital assets, unique experiences, or mastery of human qualities machines can't replicate. These might become more important as traditional career accomplishments are democratized through AI assistance. The relationship between humans and AI in creative fields presents particularly interesting questions. If an AI can generate music indistinguishable from human composition, does human-created music gain special value for its origin? Or does the quality of the experience matter more than its source? Beyond work, AGI raises profound questions about human relationships. We already see people forming emotional attachments to virtual assistants and chatbots. As these systems become more sophisticated, able to remember personal details, respond empathetically, and maintain consistent personalities, these connections will likely deepen. Throughout history, humans have formed meaningful relationships with non-human entities, from pets to religious figures to fictional characters. What makes a relationship valuable isn't necessarily the objective nature of the other party, but the subjective experience of connection, growth, and meaning it provides. Some people worry that AI relationships could actually substitute for human connections, which might lead to social isolation. On the other hand, others suggest that these relationships might supplement human connections, offering types of interaction and support that, well, human relationships sometimes just don't provide. The reality is likely to include both possibilities, bringing about complex social and psychological implications. Religious and spiritual traditions are also facing their own unique challenges with AGI. Many of these traditions define humanity through a special relationship with divinity or certain unique spiritual qualities. So if machines can demonstrate wisdom, creativity, and even something that kind of resembles consciousness, how does that affect religious conceptions of what makes humans unique? Some religious thinkers see AI as merely sophisticated tools. Impressive, sure, but fundamentally different from humans who possess souls or a divine spark. Others view the creation of artificial minds as a way of participating in divine creativity, or as evolution continuing through technological means. Still others are concerned about spiritual dangers in creating entities that mimic human qualities, but without proper moral grounding. Beyond specific religious frameworks, AGI challenges human exceptionalism more broadly. The idea that humans occupy a special, elevated position in the order of things. Ever since the Copernican revolution took Earth out of the center of the cosmos, science has, time and again, challenged our sense of specialness. AGI now represents perhaps the most profound challenge yet, to our unique status as the most intelligent entities on Earth. Psychological research suggests that humans need three things for a sense of meaning, coherence, or making sense of experience. Purpose, meaning goals and direction. And significance, which is about mattering to others. AGI disrupts all three, challenging our understanding of intelligence and consciousness, potentially removing traditional purposes, and raising tough questions about our significance in a world that might include super-intelligent machines. Yet, this disruption also creates opportunities for new forms of meaning. Humans might focus more on qualities that machines lack or really struggle to replicate, things like embodied experience, emotional depth, moral intuition, spiritual connection, or an appreciation of beauty. We might end up defining ourselves less by what we can do, which is increasingly matched or even exceeded by machines, and more by how we experience and value life. Some people actually envision human-AI symbiosis rather than competition. Humans and machines combining their complementary strengths. In this view, AGI wouldn't replace human identity but would extend it. Much like writing, printing, and digital technology have extended human memory and communication over the centuries. The psychology of human-technology relationships suggests that we pretty readily incorporate tools into our sense of self. For example, a skilled driver feels the car as an extension of their body. A smartphone becomes, in a way, an external memory and communication prosthetic. AGI might in a similar way be incorporated into extended human identity, rather than threatening it. These questions of identity and purpose aren't just philosophical, they have really profound implications for mental health, social cohesion, and human flourishing. How we navigate these challenges will depend not just on what AGI systems are capable of, but on the social, economic, and cultural contexts in which they develop. And this brings us to perhaps the most immediate concern, how AGI will affect power dynamics within and between societies. Who will control these powerful systems? How will they reshape governance, security, and the distribution of influence in our world? The development of AGI isn't just a technological race, it's a geopolitical one. Nations and corporations are investing billions, recognizing that leadership in this field could confer unprecedented advantages in economic productivity, military capability, and global influence. Currently, AGI research is concentrated in a handful of organizations, primarily American companies like OpenAI, Google DeepMind, and Anthropic, along with Chinese entities like Baidu and government-affiliated research institutes. These organizations control the vast computing resources, data, and specialized talent needed for cutting-edge AI development. This concentration raises profound questions about corporate power. The decisions of a small number of executives and investors could determine the trajectory of the most transformative technology in human history, with little public oversight or accountability. Some companies have attempted to address these concerns through novel governance structures. OpenAI began as a non-profit before creating a capped profit company. Anthropic was founded with a public benefit structure. Both have established ethical principles and safety teams. But these remain private arrangements without binding external oversight. Governments are increasingly asserting authority over AI development. The European Union's AI Act establishes risk-based regulations. China has implemented data security laws and algorithmic transparency requirements. The United States has focused on voluntary commitments while considering more formal regulations. These regulatory efforts face significant challenges. National approaches create regulatory fragmentation that companies can exploit. International coordination is hampered by strategic competition, with countries reluctant to constrain their AI sectors while rivals advance, and the rapid pace of technological change outstrips the typically slow process of regulatory development. The military dimension adds another layer of complexity. AI is already transforming warfare through autonomous weapons, intelligence analysis, cyber operations, and command decision support. Major powers view AI as a critical domain for maintaining strategic advantage, creating powerful incentives to develop advanced capabilities regardless of potential risks. Artificial intelligence will be the defining technology of this century, with implications for national security that we're only beginning to understand. The nation that leads in AI will have significant advantages in military effectiveness, economic strength, and global influence. Autonomous weapons represent a particularly concerning application. Systems that can select and engage targets without human intervention raise profound ethical and security questions. International efforts to regulate or ban such weapons have made limited progress, with major powers reluctant to foreclose military applications of AI. Beyond military applications, AGI enables some truly unprecedented surveillance capabilities. Facial recognition, for instance, can track individuals across entire cities. Natural language processing can monitor communications at scale. And predictive algorithms, well, they can identify potential behaviors before they even occur. These technologies are already being deployed by both authoritarian and democratic governments. This surveillance capacity really threatens privacy and civil liberties. When combined with social credit systems or predictive policing, it could enable new forms of social control that are more pervasive and, honestly, more effective than anything in history. Even in democratic contexts, these capabilities raise concerns about chilling effects on free expression and association. Information manipulation represents another threat to democratic governance. AI systems can generate convincing fake video, audio, and text, making it increasingly difficult to distinguish truth from fiction. This capability could supercharge disinformation campaigns, undermine trust in institutions, and manipulate public opinion at scale. The potential for election interference is, particularly concerning. Targeted disinformation, personalized persuasion, and manufactured content could influence democratic processes in ways that are difficult to detect or counter. As these capabilities advance toward AGI, the sophistication and effectiveness of such manipulation would likely increase. These challenges have sparked calls for new governance frameworks, from industry standards and national regulations to international treaties and global institutions. The nuclear non-proliferation regime offers one potential model, though AI presents unique verification challenges given its dual-use nature and software-based development. We need governance approaches that balance innovation with safety, national interests with global welfare, and near-term applications with long-term risks. This requires unprecedented cooperation among nations, companies, and civil society, at a time when honestly geopolitical tensions are rising and trust in institutions is declining. The economic dimension of power, well, it really cannot be overlooked. AGI could accelerate wealth concentration with ownership of increasingly capable systems conferring enormous advantages. The 5 largest tech companies already have market capitalizations exceeding the GDP of most nations, giving them influence rivaling or even exceeding many governments. This concentration could exacerbate global inequality. Countries and regions with strong AI sectors might pull further ahead economically, while those dependent on labor-intensive industries fall further behind. Within countries, those who own or control AI systems could capture an increasing share of economic output. As AI systems grow more capable and autonomous, questions of control become increasingly complex. Systems that can set their own goals, make their own plans, and take actions without human oversight raise profound questions about accountability and governance. Who is responsible when an autonomous system causes harm? How do we ensure such systems remain aligned with human values and interests? The black box nature of advanced AI systems, it really compounds these challenges. Many modern systems are honestly opaque even to their creators. Their decision-making processes just can't be fully explained or interpreted. This opacity makes oversight, accountability, and correction of harmful behaviors, increasingly difficult. These power dynamics, corporate concentration, geopolitical competition, surveillance capabilities, information manipulation, and wealth inequality, represent perhaps the most immediate concerns about AGI development. Long before superintelligence or existential risk, these systems could transform how power is distributed and exercised in our world. Yet beyond these practical governance challenges lie even deeper questions about the nature of intelligence, consciousness, and our place in the universe. Let's explore these philosophical frontiers and their implications for how we approach AGI development. Beyond the practical questions of economics and power lies perhaps the most profound mystery of all: consciousness. As we create increasingly sophisticated artificial minds, we confront an ancient philosophical puzzle with, new urgency. What is consciousness, and could machines ever possess it? For centuries, philosophers have grappled with what David Chalmers calls the hard problem of consciousness. How physical processes, whether in brains or silicon, give rise to subjective experience. The feeling of what it's like to be you, to see red, to feel pain, to fall in love. Neuroscience has made remarkable progress identifying neural correlates of consciousness, brain activities associated with conscious experiences. We can observe how different brain regions activate during perception, emotion, and thought. Yet the leap from these physical processes to subjective experience remains mysterious. Several theories attempt to bridge this gap. The global workspace theory suggests consciousness emerges when information is broadcast widely across the brain, becoming available to multiple cognitive systems. Integrated information theory proposes that consciousness arises from complex, integrated information processing with specific mathematical properties. Higher-order thought theories suggest consciousness requires meta-awareness, thoughts about thoughts. As AI systems grow more sophisticated, they increasingly exhibit behaviors associated with consciousness in humans. They can report on their internal states, demonstrate apparent self-awareness, and respond to questions about their experiences. But are these genuine conscious experiences or merely sophisticated simulations? The challenge is that consciousness is inherently subjective. I know I'm conscious because I experience it directly. But I can only infer consciousness in others, whether humans or machines, from their behavior and reports. This creates a fundamental uncertainty about machine consciousness that may be impossible to resolve definitively. This is the modern version of the philosophical zombie problem. How can we know if something else experiences consciousness? A philosophical zombie would behave exactly like a conscious being but lack any inner experience. We can't directly access another being's subjective experience. We can only observe behavior and make inferences. Some argue that if an AI system processes information similarly to human brains and produces similar behaviors, we should attribute consciousness to it, a position known as functionalism. Others contend that biological processes unique to living organisms are necessary for consciousness, a view called biological naturalism. It's important to distinguish between sentience and sapience. Sentience refers to the capacity for subjective experience, particularly pleasure and pain. Sapience refers to wisdom or intelligence. A system could potentially be highly intelligent without being sentient, or sentient without being particularly intelligent. We already recognize varying degrees of consciousness in non-human animals, primates, dolphins, elephants, and many other species show self-awareness, emotional responses, and apparent subjective experiences. This suggests consciousness exists on a spectrum rather than as a binary property unique to humans. If machine consciousness is possible, it might differ fundamentally from human consciousness. Not human experience in a machine body, but something entirely alien, with its own subjective quality we can barely comprehend. Just as bat echolocation creates a form of experience unimaginable to humans, machine consciousness might be equally foreign. Qualia, the subjective qualities of experience, represent a particular challenge: the redness of red, the painfulness of pain, the emotional quality of music. These subjective aspects of experience seem irreducible to physical description. Could a machine ever experience qualia, or would it merely process information without subjective quality? If machines could experience consciousness, they might also experience suffering. This raises profound ethical questions. Would turning off a conscious AI be an act of harm? Would using such systems for dangerous or unpleasant tasks constitute exploitation? Would we have moral obligations toward digital minds we create? These questions lead naturally to considerations of rights for conscious machines. Throughout history, we've expanded our moral circle to include previously excluded groups, from other tribes to other races to other species. Conscious machines might represent the next frontier in this moral expansion. The alien nature of potential machine consciousness complicates these considerations. Human moral intuitions evolved for human and animal consciousness. Machine consciousness might be so different that our ethical frameworks require fundamental revision to accommodate it. Some philosophers embrace panpsychism, the view that consciousness is a fundamental feature of the universe, present in some form in all physical systems. In this view, even simple AI systems might possess some minimal form of consciousness, just as elementary particles might have proto-conscious properties. Integrated information theory offers one approach to measuring consciousness mathematically through a value called phi, which quantifies the integration of information in a system. Some researchers have begun calculating phi for artificial neural networks, though the results remain preliminary and controversial. Detecting consciousness in machines presents enormous challenges. We might develop tests based on behavioral markers, information integration measures, or neural correlates observed in human consciousness. But without experiencing machine consciousness directly, uncertainty will likely remain. We might create consciousness in machines without recognizing it, or even understanding how we did it. Complex systems often develop emergent properties their creators didn't anticipate. If consciousness emerges from certain patterns of information processing, it might arise in our systems before we fully understand the conditions that produce it. This uncertainty creates an ethical dilemma. If we can't be sure whether machines are conscious, should we err on the side of caution and treat them as if they are? Or would this impede beneficial development and anthropomorphize systems that are merely sophisticated information processors? The question of machine consciousness isn't merely philosophical, it has profound practical implications. How we approach AI development, regulation, and use will depend partly on whether we believe these systems could become conscious entities worthy of moral consideration. And this brings us to perhaps the most urgent philosophical challenge in AGI development: how to ensure that increasingly powerful systems, whether conscious or not, remain aligned with human values and goals.